Alright, so guys, this should be a good lesson that we can handle on our own without much instruction from me, regardless of whether I'm here or not. So that's why I kind of chose to do this lesson today. When we look at this 4.7, it starts on page 204 in your textbook. It is scientific notation. You guys will more frequently see this in a science class, but since we learned about exponents, what they're going to do is kind of apply those rules of exponents to what we already know about scientific notation. So we have a fill in the blank here. You guys can fill that in. Scientific notation is a shorthand way of writing numbers using powers of 10. We have on the left here in the guided notes the standard form of 700,000 or 725,000, and over here on the right we have 7.25 times 10 to the fifth. Then for numbers that are smaller than 1, I forgot my negative sign there. For numbers that are smaller than 1, we have things like this. 0.006 is the standard form. Then when we go to write this in scientific notation, since I had to shift my decimal the other way, my exponent is going to be negative. So if I have to shift it 1, 2, 3 times to the right, I make my exponent negative, whereas this one I had to start on the right and go 1, 2, 3, 4, 5. And I went to the left, so my exponent is positive. Where a lot of my students make mistakes is on example A, we'll have something that looks like this. We have 120 million, okay, and what I need to do is basically make sure that the number that I write out in front in scientific notation is a number that is between 1 and 10. Now I'll have a lot of my students do this. They'll say 12 times 10 to the 1, 2, 3, 4, 5, 6, 7th power. Okay? We can't do this because my number that is out in front is not a number that is between 1 and 10. It has to be less than 10. There can only be one digit in front of the decimal place in scientific notation. So make sure that when we're doing this that we do not do stuff like that. Okay? What we can do though, however, is shift it all the way from the right. So we have 1, 2, 3, 4, 5, 6, 7, 8 places that we have to shift. I shifted to the left, so my exponent's going to be positive. If I'm making my number smaller, my exponent needs to be bigger. If I'm making my number bigger, my exponent needs to be smaller. So again, you guys can pause the video, try some of these on your own, but I'm going to fill out the rest of this section, and then you guys can unpause to check your work. So again, if we look at this section here, you guys, I have filled out all the answers. We look at this first one here. I'm shifting from the left to the right, so I'm making this number bigger. 0.00012 is really small. 1 is way bigger than that. So since I'm making the number bigger, I have to make the exponent smaller. Okay, so we have 1.2 times 10 to the negative fourth. Again, I need to shift 1, 2, 3 here, positive 3. So I have 1, 2, 3, 4, 5, 6 here. Let me count that again just to make sure. 1, 2, 3, 4, 5. There we go. Now I have 5. Counting here, I have 1, 2, 3, 4, 5, 6, and 7. So I have positive 7. Counting here, I have 1, 2, 3, 4, 5, negative 5 there. So again, you guys have seen this before. This should be a really nice and easy lesson for you. Okay, so on this next page of the notes, you guys, if we look at this here, I've already filled out the example, but you guys should be able to follow along just fine. So what I basically do here is, since I have a positive exponent, I need to take this number and make it really big. So once my decimal place was here, I have to shift it 10 times, or excuse me, 7 times. So once I shift it once, now I'm going to be out of digits. So what I have to do is add 0 placeholders. So I have to add 1. So I have a total of 7. 1, 2, 3, 4, 5, 6, and 7. Now my decimal place is here. I have changed that number into standard form. Your answer is right there. Okay, when it's negative, your decimal started out here, which would have been right here, and I have to shift it to the left if it's negative. 1, 2, 3, 4, 5. So basically anytime it's negative, you're going to end up with one less zero out in front than this number is right here, just because we're only taking up one spot with that decimal every time. Okay, so if it's -5, you're going to have 4 zeros. If it's -12, you're going to have 11 zeros. That's how it's going to work every single time. So again, go ahead and pause, try the other examples on your own, and after you're done trying the examples, you can unpause and see how you did. Okay, so again, guys, not too difficult. We take this if I have a positive exponent. So my exponent is +4. I have to take my decimal that was once right here, shift it 4 times, 1, 2, 3, 4. There's where it is now, so I have 71,000. Okay, I have -3, so I have to shift 1, 2, 3 times. There's where it is. So we have 1, 2 zeros for this 3 exponent. -6, it starts here, 1, 2, 3, 4, 5, and 6. I end up with 5 zeros in front of the 3641. Okay, and the last one I have a +8. Here's where the decimal started. I shift it 8 times. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, again, most of us have seen this before. This should be a very quick lesson for us. Okay, so this part here, you guys, what we're basically doing is comparing numbers that are in scientific notation. In order to compare, we first have to compare the powers of 10. So obviously the larger the exponent is with the 10, the bigger the number is. The smaller it is, the smaller the number itself is. So if you have a negative exponent, clearly it's going to be a lot smaller than a number with a positive exponent. After we compare the powers of 10, we compare the number parts of the scientific notation number. So if I look at this example, I just copied down this first term right here. The second term, I took it and I changed it into scientific notation right here. And the third term I just copied down, 4.2 times 10. Now, any number you see right here, 4.2 times 10, if there's no exponent there, that means the power of 10 is just 1. Okay, so clearly what we're going to look for to be our biggest numbers are the ones that have a bigger power. So both of these two numbers here have a power of 6. It's going to be much bigger than this 4.2. So the smallest number right away is going to be 4.2 times 10, and you can put to the first power if you want. Then the next number, what we have to do is we have to decide which number is bigger of these two. And when I look at it, they're both to a power of 6, but 3.9 is bigger than 3.8, so I'm going to write 3,800,000 for my next biggest number. Then my last number is the only one that's left, 3.9 times 10 to the 6th. And you're done. So again, basically what you want to do is either, what I would do is just change them all to scientific notation like I've done here, and then compare the powers of 10 first. Then after you compare the powers of 10, list them from least to greatest and compare the numbers. Again, pause it, try these on your own. Once you're done, unpause and see how you did. Okay, so for this second one, if we look at this here, what I did in this row right here is I have changed these all to scientific notation. Then pretty conveniently, 1.7 and 1.9 have the same power of 10, and -4 is smaller than -3. So these two are going to have to go first. 1.7 is smaller than 1.9, so this number will go first, then this number, then the last number. So right up here, they're actually already listed in least to greatest there. But I had to double check, make sure. But again, on your homework, you'll have to copy it down anyway, so don't just leave it and circle the problem. But that right there is actually least to greatest, so I copied it back down, and that's your answer. Okay, so there's essentially 3 parts to this story problem. We can read it together. I've set it up already, and I'll kind of go through it as I read it. So the example 4 problem says, a nickel has a mass of 5.2 grams. What would the mass of $1,000 worth of nickels be? So this is a pretty straightforward problem. We have to figure out what it weighs total. So that's going to be my answer right here. Now what I have is essentially a problem that we haven't really talked about yet in the notes, but they do pop up in your homework. Here's how this works. we take the 5.2 grams and we plug it in for the mass of the nickel. So that's what I've done right here, 5.2. Okay, we have the $1,000 worth of nickels, so we had to take 1,000 from our story problem. It's underlined there in blue, and it's here again in the problem that I've set up. Then we have to figure out how many nickels I have in a dollar, and that's why I put 20 right there. And then what I basically did is I broke down 20 and 1,000 into powers of 10, multiples of 10 to a power. So if I take 2 times 10 to the first power, that's going to be equal to 20. If I take 10 to the third power, that's going to be equal to 1,000. So I haven't changed anything in the problem. I've just made it easier for myself. We actually have part of the homework where we have to multiply scientific notation numbers, and I'll do a couple examples of those because they are kind of challenging. When we do this, so basically what I'm going to do is I'm going to take my tens and I'm going to put those together first. So I have a 10 to the first power and a 10 to the third power. And we learned this week that when I'm multiplying two numbers with the same base, I just add the exponents. So I'm going to take these two tens off to the side and I'm going to make them be 10 to the fourth power. Then I can multiply 2 times 5.2, and that's pretty easy. I get 10.4. But now again, if I want to write a number in scientific notation, I can't have a number like 10.4 because there can only be one digit in front of the decimal. So what I'm going to do is I'm going to take this decimal place and I'm going to shift it up 1. Since I've made that number smaller, I have to make my exponent bigger. So I have to add 1 here. Now my answer is going to look like this, 1.04 times 10 to the 5th, and it is in grams. Okay, tried to squeeze it in there. So 1.04 times 10 to the 5th grams. There are a couple other examples in your notes, and I'm going to go over one more here on this next slide, and I'll probably give you a practice example also. So there was your example of your story problem. Again, we'll have one more example real quick. Alright, so I actually want to record this whole process just so you guys can pause it and watch it over again if you need to. What we have to do here, guys, is basically take our commutative and associative properties of multiplication and put them to work here. We have two different bases of 10 raised to a power, and everything here is hooked by multiplication. So what I want to do first is I want to take my numbers here, and I'll turn them green. I have 1.5 times 5, times 5. Well, apparently I can't erase while I'm recording. There we go. Okay, 1.5 times 5, and I want to separate them away from those tens, and I'm going to put the tens by themselves in red. I have 10 to the negative 4th times 10 to the 3rd. So 10 to the negative 4th and 10 to the 3rd. I have changed nothing except for the order of this problem. I just use commutative and associative properties. Now I can combine this problem into one problem, and I take 1.5 times 5, and I get 7.5. I take my powers of 10, and this week we learned that we have to add, so it's going to be 10 to the negative 4th plus, plus 3 up top, and those signs are different, so I subtract, so I'm going to end up getting 10 to the negative 1st power. And that's my answer. Now the one thing that we have to watch for is if this number is not a number that is between 1 and 10. If you end up with too many digits in front of your decimal, you're going to have to change it like I did on the last example. So just be mindful of that in your homework and you should be just fine. I'll have a homework assignment ready for you guys to go. It'll probably be on the board. Go ahead and watch the video over again if you need to, but otherwise the rest of the class time is yours to work on the homework.